Hello, everyone. My name is Zhangchen, and I'm now a second-year PhD student in Network Security Lab, University of Washington. Today, I'm glad to introduce my work called ACE, a model poisoning attack on contribution evaluation method in federated learning. So this is the outline of my today's presentation. I will first introduce federated learning and also come to a subfield of federated learning called contribution evaluation. Then I will show the threat model and the detailed design of our model poisoning attack to contribution evaluation. We call it ACE. Next, I will show the experimental result of ACE against 5 state-of-the-art contribution evaluation method and the existing countermeasures. And finally, I will conclude my presentation and discuss the potential future work. So the federated learning has emerged as a promising solution to enable privacy-preserving machine learning, which enables collaborative train a machine learning model while also keeps the data locally. And it already has many real-world applications from the keyboard in the mobile phones to collaboration among big companies to train maybe large language models. And here is the paradigm of the current federated learning. There are two kinds of participants. One is a client who are data owners, and another is a server who help to coordinate the training process. And in step 0, both server and client will initialize the same model. And in step 1, the client will update the local models using their training data set. After that, it will send the local model update back to the server, and the server will try to aggregate a new global model and return back to the client. The step 1 and 1, 2, 3 will do iteratively until the model reaches the convergence. And in federated learning, data quality is quite important to ensure the success of federated learning. So we need to ensure that the clients with high amount and high quality data to continuously participate in federated learning. Therefore, the incentive mechanism has been proposed to solve this issue. The key idea of the incentive mechanism is to have a contribution evaluation method, which will assign different contribution to different clients based on its performance during the training. And the reward will be assigned based on the contribution of each client. So the existing studies usually primarily focus on the development of new metrics or algorithm to measure the contributions. But we are the security researchers, so the security of contribution evaluation in federated learning is actually not well explored. Here we have a key observation of the contribution evaluation method. That is, the server doesn't have raw data because of the federated learning nature. So the contribution cannot be measured directly using the data quality. So usually this contribution evaluation method will use the local model update to measure the contribution. So this unique feature may be leveraged by the malicious client by sending some carefully manipulated local model updates. So our research question is, can a malicious client processing some low-quality data elevate its contribution to evaluate by the server, and how? Here is the threat model of our paper. The attacker is a client in federated learning who process low-quality training data, and it can access to the local training data sets, the global model, as well as control the whole training process. And it can also manipulate the local model update before sending it back to the server. So we call this attack a model poisoning attack. And the attacker's objective is to maximize the contribution of a local model update evaluated by a certain evaluation method deployed in the server. And we have the following 4 design goals. The first goal is effective. That is to increase the contribution as demonstrated in the attacker's objective. And the second design goal is universal. That is, we want our method to be agnostic to any aggregation rules and the contribution evaluation method. And the third design goal is the performance preserving. That is, to preserve the final performance of the global model, because the attacker may also want to use that global model to do his own job. And the last thing is efficiency. That is, we want our method to be as efficient as possible. Basically to be comparable with training using its own data set. And before coming into the detailed design of ACE, let's first look through current contribution evaluation method. There are 2 main categories. The first category is called individual evaluation-based method, and there are 2 measurements that are widely used. The first measurement is called cosine similarity between a local model update and global model update. And basically, if the cosine similarity of local updates and global updates are higher, which means the contribution of that client will be higher. And there's another more straightforward way to calculate, that is to use a validation data set, where the server obtains a validation data set and use it to calculate the validation accuracy or loss to evaluate the contribution. If the model has a higher accuracy, then its contribution should be higher, quite straightforward. And instead of calculating the contribution one by one, we also have some joint evaluation method, which consider the influence when we have a certain client in the group or not. The first one is called marginal loss, or some other researchers call leave one out, that calculates the differences between client join and leave. And another is Sharpley value come from economics, which calculates every subset of clients and gets the average gain of each client when it joins the group or not. However, although this one is successfully in benign case, those contribution evaluation methods may fail to realize that due to the iterative nature of federated learning, actually the aggregated global model will contain the information of other high-quality clients. So the attacker can actually leverage this information to help it get a better local model update and hence hack the reward and get a higher reward value. So specifically, we leverage this information by mimicking the global model updates using the historical information of past global models. And we propose a two-step pipeline to perform the attack. So in step one, we want to do the future global model prediction by using the Cauchy mean value theorem. Here, the GT is the model we want to predict, and we can use the previous global model update plus a Hessian times the difference of two global models. And here, computing Hessian is quite time-consuming, so we use LBFGS algorithm to efficiently estimate it. Here we note that all the inputs to the LBFGS algorithm are within the attacker's knowledge, so the attacker can successfully predict the next global model. And please refer to our paper for detail if you are interested in that. And for the second step, we note that solely predict the future global model may not be enough to accurately predict. So we also propose a threshold-based filtering algorithm, where we have the insight that the global model updates across different iterations should have similar scale. So we just limit the norm of the LBFGS, and if the norm is less than a threshold, we think the error is tolerable. In our paper, we also propose some strategies to further enhance our proposed ACE based on either cosine similarity-based method or the validation data-based method. And also please refer to our paper for details. Here is the experimental setup for our paper. We conducted the experiment to evaluate the effective of ACE by using 3 data sets, 2 models, as well as 3 data partitions. Here, the uniform distribution is identical and independent and identical distributed case where the same data amount, we have the same data amount and quality across different clients. And the power law distribution differs in the amount of data of different clients. And the class imbalance differs in the class labels of different clients. And we also evaluate our attack using 5 state-of-the-art contribution evaluation methods, including FedSV, LO, CFFL, GDR, and RFFL, which spans both joint evaluation-based method and individual evaluation-based method. And since there is no previous attack on contribution evaluation, we also modified some existing model Poisson attack from the literature, including delta weight attack, scaling attack, and also data augmentation as our baselines. So the evaluation, we also designed several evaluation metrics to reflect our design goal. To evaluate the effectiveness, the first metric is to calculate the normalized contribution score by sum all the contributions across round and get the normalized score. And we also calculate the rank gain, that is a rank difference of a certain client before and after applying our ACE algorithm. For example, if the rank of a client is 10, which is the lowest if we have only 10 clients, and after ACE it increases to 1, then the rank gain is 9. And for showing the performance preserving, we use the test accuracy, and for showing the efficiency, we use the ratio between the computational cost of using training data set and our ACE. So the first takeaway of our experiment is that ACE is effective and universal across different kind of data sets, data distribution, as well as different kind of contribution evaluation method. Let's just amplify that. Here is an example of one in the scenario of class imbalance, heterogeneous data distribution, and we use CFFL as contribution evaluation method and use tiny image net to train the machine learning model, and we find that all baselines fail to increase the contributions, but our ACE can still successfully increase the contribution, indicating our method is more effective than other baselines. And the second takeaway is that ACE can preserve the utility and also amplify that. We can find that compared with no attack, our ACE can have similar test accuracy across all settings, indicating that it can indeed preserve the utility. And we also show that ACE is efficient. As you can see from this table, the speed of ACE is at least seven times faster than training using its own data set. We also evaluate ACE against 6 countermeasures to model poisoning attack, including trimmed mean chrome, multi-chrome, and so on. And we find that ACE is stealthy against state-of-the-art defense. So in conclusion, we find that current contribution evaluation method in federated learning can be easily attacked by malicious clients. To do so, we propose ACE, a model poisoning attack to contribution evaluation in federated learning, which can successfully elevate the malicious client's contributions. And from our experiment, we show that ACE is effective, preserves utility, efficient, and also quite universal. And we also show that current countermeasures may fail to defend against ACE. That's why new mitigation strategies may need to be deployed as a future work. And this is the collaborators of this work from UW, Penn State, and UChicago, and the work is supported by these funding agencies, and we would like to acknowledge their help in supporting this project. And here are the references of my talk. And thank you for your listening, and I would like to answer any question you may have.